Everyone, today is going to be an introduction to Chapter 6. And congratulations, everyone. You are now two chapters away from finishing. And just to give you an idea of where we're going, Chapter 6 and Chapter 7 are sort of under the same umbrella. We are basically looking at patterns and patterning, looking at different ways we can identify patterns, and then looking at different ways we can express it, like writing a formula or an equation to represent the pattern. And then once we are able to do that very well, we are basically applying this knowledge to um, things like finances. So chapter 7 is all about finances and money and how that can grow. And that sort of makes sense because if you want to make money grow, um, if you want to make money grow, we want to sort of have a way to predict, like if I put in, $10 away every month, what does that grow into in 40 years? Something like that. Um, so just keep an eye out. Just be open-minded. I want to use this opportunity as a plug to talk about where we're going with this as from a teacher's perspective. Amina and Saima, I got you. I just wrote you as absent, so you might get a phone call, but I took it right off. So hopefully you can ignore that and your parents don't get confused. Okay. Okay. Back to the topic on where we're going. Um, my goal, and I've been talking about this throughout the year. I I understand that not everyone's going to pursue mathematics, and I'm not selfish for my students for to all my students must do grade 12 math. No, that's not what I'm saying. Um, if there is one thing that you will take from this course, I hope that it is to be able to look at a particular situation and have the eyes to apply numbers to it to better help your situation, to make processing something a lot easier. Math really helps to do that, to take a complex situation and organize it and see it in a way that makes sense. And the next step out of that is to do something about it so that you're in a better situation than before, just to help your life. And the second thing that I hope that you take from my course is the final optional assignment that I'm going to give you for chapter 7. Even if you don't pursue math, money is going to be something that is a big part of your life, whether we like it or not. Unless we go into some kind of like communist country where everyone is equal, right, as comrades or whatever, we have to deal with money. Money is a tool. Yes, money won't necessarily buy you happiness, or yet money isn't everything in the world, but you can't separate yourself from money because of the way the world works, and so you need to be responsible for it. I firmly believe that it is something that I would have appreciated if my teacher taught me in grade 11, or even my parents taught me in when I was younger. So I hope that it will be useful to you. And when you see it, when you do the assignment, and and the goal is that it clicks and your eyes are open, that you will become that much more financially responsible and start hustling and make moves and realize that as long as I do this minimum amount, I can actually be comfortable when I get older. And what I mean by that is, I just want to tell a quick story. I know I'm sort of rambling here, but um, you might have had your parents or guardians talk about money a lot, right? Whether you're rich or you're poor, money is never going to be completely out of the picture. It will come up as a discussion. Your parents might teach you about money, parents might complain about money, parents will talk about money where you're, paying a mortgage for a home or whatnot. Josh, you are here. Let me take a look. Yeah, I got you though. You might get a phone call, so just ignore that, okay? Um, Same with you, Zoe. I got you now. If you get a phone call, just ignore it. I have you as present. So again, going back to the idea of money, I first learned about money. I was a young professional. I was in my low 20s. I was a young Thundercat, looking good, feeling good, feeling smart, feeling nice about myself. I got my first job and, making good money just because it's my first paycheck. I don't have to pay for homes. I don't have to pay for anything, just maybe my car. Um, but interestingly enough, my parents, as opposed to having conversations about money, they're just like, all right, we didn't get a chance to talk about money or teach you about money per se because we were busy making money ourselves because we were an immigrant family. As a way to learn through experience, learn by burning it into my body. My parents forced me and my two older sisters to give them 500 bucks a month out of our paycheck. And me being, a young guy, I'm just like, yo, I got places to go, I got people to see, I got parties to attend to, I got things to buy. The list went on, but my parents were like, no, spend money, spend whatever you want, but first pay yourself by giving me 500 bucks a month. I'm just like, why? What they were trying to do was using their name and their credit, they pulled out a mortgage for us, and we basically, me and my two sisters, so three owners, bought a house together. So in my young 20s, I was the owner of a house, a co-owner of a house. And that was crazy. And I didn't see the money, I just saw money disappearing. But when the time came when I was late 20s and my parents are like, now is a good time in the market to cash out, and we sold the house, I had a fat stack of cash in my bank account. Um, it was impressive. And from there, I'm like, how did this happen? And then the conversation opened up of, well, money, putting in 500 bucks a month, did this, did this, did this, did this. And as you were paying it off, your asset was growing in this way. And we talked about equity, just went on and on and on. You may or may not have that privilege to have that kind of conversation or even have a chance to go through that experience, having parents and multiple siblings and to pool money together and decide to buy a house without legal repercussions, right? I just want to say that that kind of experience aside, I really hope everyone finds it in them to dig deep and do this optional assignment because I firmly believe it will change your life and how you see the future, how you how responsible you become with money. On the internet, you hear about this FIRE movement, right? What is it? Financially independent, retire early, or something like that, like FIRE. And what does it mean, and how do we get there? And all of that will start to make sense if you do the assignment. Okay, so I talk a big game right now, and I'm trying to, what's the word that you guys use? Gas up the assignment right now. Okay, that's what I'm trying to do. But I really hope that you will go through with me. We're gonna start with chapter 6, which is really boring. It's gonna be easy, but it's boring. I like you to go through and really pay as much attention, really put some effort into chapter 6 because it builds into chapter 7. Um, and yeah, and the rest is history. Yeah, I'm recording right now. Okay. Please, please, please give it a shot. And yeah, let's get to it. To start off, chapter 6, 1 and 6.1 and 6.2 is sort of part of the same idea. I'm going to go through some patterns with you, try to get you to warm up to it, and then I have to talk about some new definitions because we're going to be throwing these definitions around a lot when we look at patterns. Um, yeah, and lastly, of course, I need to make sure everyone has their calculator as we approach chapter 7 because chapter 7 is largely just um, plugging in formulas, financial stuff. Okay? Okay, let's get started. I talked a lot. Any questions before we begin? Okay, let's do this. Starting off, can you identify the pattern in the following sequence of numbers? And already I'm starting to use a slightly different terminology here. Sequence is another way of saying just a set of numbers that go on and on and on. This is a sequence of numbers, okay? A set of numbers that have a relationship with them. So, what's the pattern? And I'll tell you right now, there could be more than one way to express it. Someone want to volunteer their time? Going once, Wait, twice. Thanks, Murdoch. 3. The idea, I believe, what he was trying to say is every step of the way along this sequence, I am adding a 3. Correct. Is there another way you can express it? Think about it. I'm going to take Murdoch's idea, and if I were to write this as a function, you can say that I am taking the number 3 and I'm adding another 3 every step of the way. And so how many 3's am I doing? I am adding 3 times how many times, right? So we'll talk about it in just a second here. Anyone else have a different way of writing it? Instead of adding 3, you can say something else. No? You can also say that each number here is a multiple of 3, right? The first one is basically 3 times 1. The second is also 3 times 2. The third, it would be 3 times 3, so on and so forth. So what we are drawing here, it will be 3 times the variable n. What I have written here is what we call a discrete function. By discrete, I mean, take a look at the numbers that I'm plugging in. Did I plug in any decimals? Is there such a thing as the 1.5th number in between the first number and the second number? No. A discrete function, if I were to put it in a graph, is not a curve or nor is it a dotted line. I mean, nor is it a solid line. There is space between it because I don't care about the decimals. It's literally just 1, 2, 3, 4, and 5, and I made an error. There isn't even a 0. A discrete function, we are looking at sequences where the first number we or the I guess the pattern we give it we start with the first number, right? Like this is n. It's going to belong to natural numbers. Like when we look at this sequence of numbers, we don't say that this is the 0th number and that's the first number. No, in a sequence, we're like, hey, what's the first number in the sequence? It just very casually say it. This would be my first number. That is my second number. And that is my third number, so on and so forth. You notice how we casually say the first number instead of the 0th number? That is because we refer to a discrete function as a sequence where the term begins at the number 1. Okay? I don't mean to confuse. We just say it's a discrete function, there's no decimals, and we start at 1. Okay? Another term I'd like you to know is the word term. Now, in mathematics, term is basically a number. So if I have a polynomial or trinomial, this is one term, that is one term, and this is one term. That's one number, that's another number, and that's another number. For a sequence, a term is exactly the same thing. It is a certain value that is placed in a sequence. So in this case, if I say something like term, we can refer to it as just Tn, and we say, hey, what's the term? Well, in this case, the first term is a 3. The second term in this sequence is a 6. The third term in the sequence is a 9, and so on and so forth, right? So T stands for the term, and the little subscript n refers to, hey, which location are you going to find this number? Like which place in this sequence is it? Which brings us to the term number n. This n that I wrote here is what we call the term number. It refers to the place in line on the term is found in the sequence. So where in the sequence is this term found? This one right here, the number 3, is found in is the first term. It's found at the very beginning. Okay. T2, term 2, literally is 6, and we say that's the second term. And that is the third term. The value is a 9. So the term itself is the value that you see in the sequence. The term number refers to where in the sequence will you find that value. So in this case, n equals a 1, this n is a 2, and that n is a 3. Why do we refer to this new kind of notation? Well, the fact of the matter is, because we're looking at patterns, we really don't care whether this is going to be a proper function or not. Right? We really don't. It's not on a graph. What we're looking at specifically is the pattern, a sequence of numbers, a set of numbers. And so instead of writing f of n, this actually limits us a bit, right? It's too complicated to talk about a function when we can't even use negatives or we can't even use a 0. And so instead of that, we refer to these sequences and we write an explicit formula, not a function, and we simply define an equation as Tn. So the general term for this sequence, as we wrote here, would be 3 multiplied by whatever the term number is. So T1 means, hey, what's the first term? Well, that means the term number is a 1, so I'm going to multiply with that. The value is a 3. Hey, what's term number 2? Well, term number 2 means my n value is a 2. 3 times 2, that's a 6. And it matches, right? T2 is 6. What is term number 3? Well, that means my n value is a 3, so 3 times 3 is a 9, and that matches with my sequence. So long story short, we could write it as a function, but we don't. We write the equation in terms of the general term Tn, where you have to define what n is, and then you end up just plugging it in. Any questions about these definitions? You're going to be using them left, right, and center, so even if you don't quite get it, it's okay. You'll get a chance to see. Who else made it? Amina made it. Great. Let me fix that attendance. Amina, Mohanad as well. You might see attendance. You might get a phone call, but just ignore it. Helen is, I do not see. I hope she's okay. Anything else? Zane T. Is Lucas here? Zane D is here. Great. Jonah and Lucas. Lucas is not here. Jonah's not here. Okay, I'm going to move on. Okay, if there are no other questions, I am going to go ahead and start talking about an introduction to discrete functions. So I'm doing 6.1 and 6.2 together. They're basically the same thing, but expressed differently. So there are some definitions where sequence, term, explicit formula, continuous, discrete, and all this that you see on the screen is basically in case you missed the class or you wanted an extra sort of detail about it. Okay, here we go. So if we're dealing with a discrete function, f of n equals 2n plus 1, because we know it's a discrete function, all the values that we're plugging into this function are going to belong to natural numbers. So we start with a 1. Okay? So f of 1 is 2 times 1 plus 1, that's a 3. 2 times 2 plus 1, that's a 5. And 2 times 3 plus 1, that's a 7. So my sequence would be 3, 5, 7, dot, 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 dot. And see, I'm doing definitions again. Each number in this sequence, we call it a term. And also, instead of writing it as a function, we like to write it in terms of a general formula, or in this case, an explicit formula. Tn is equal to 2n plus 1. Monad, I got you. Monad, sorry, if you do get a call from the machine, um, the automatic system, just ignore it. I have you as present. Lucas, you made it. Yes, I do need to change you. There you are. I know, Lucas, today we're supposed to start at 1:35. Kinda, you made it. But that's okay. Kinda, I have you. That's great. I think I saw you. Oh, Jonah made it too. Okay, okay. Yeah, so I figured it's not because you guys were missing per se. It was just, yeah, you guys probably didn't know. Okay, you didn't miss much. And if you want to get into it, what you missed was basically me trying to really inspire you. Oops, oops. I just cleared everything. Inspire you to do the final optional assignment. Okay, so if you want to see me talk about, some stories about myself when I was younger, as an analogy, go ahead and watch the YouTube video. All right, all right. If you are okay with the notation, I'm gonna give you like 30 seconds. Could you solve, find the first three terms, in other words, n equals 1, 2, and 3, for the following explicit formulas? So please find T1, T2, and T3. And T1, T2, T3. I'd like you to try it in no time. I'm going to give you 30 seconds or so, maybe a minute, just because it's a bunch of stuff. Hmm. All right. So the first one, if n is a 1, n cubed minus 1, that's a 0. If it's a 2, that's 2 cubed, that's a 8 minus 1, that's a 7. And 3 cubed minus 1 is a 26. So if this was a sequence, you would write it just like that, right? It doesn't seem like there's much of a pattern, but, well, there it is. T1, 2 to the power of 1 times half, that's a 1. That is 2, 4 divided by 2, that's a 2. 2, 3, that's an 8 divided by 2, that's a 4. So 1, 2, 4. That's a little easier to see as a pattern. And lastly, if n equals 1, 1 minus 1, that would be a 0. 2 minus 1 squared, that's a 1. And 3 minus 1 is a 2 squared, that's a 4. 0, 1, 4, comma, dot, dot, dot. Okay? So this is how we do explicit formula. Um, Once you get a hang of n equals, in other words, you can use n as a resource in an equation like this, or like this, or like this, you realize there's a lot of different ways you can express the same combination. Like, would you have expressed this for this sequence? I wouldn't. I would have a different equation for that, right? Same with this one, 0, 1, 4. Would you have written in this way? Maybe. But this is what I mean. 6.1 is, as an introduction, just learning how to express patterns using a formula. So go ahead. Would you try writing an explicit formula for Tn for each of these sequences? I'll give you about a minute. I'm going to pause this video for a minute before I restart. Okay, Simon, let's pretend we didn't say anything. Can anyone can anyone suggest their pattern, please?
Okay, m plus 1.
Okay, so think carefully about this. If I say term 1, right, that means my n value is 1. So if it's actually n plus 1, that's actually saying 1 plus 1. The answer should be a 2. But my first term is 1. How about we revise it a little bit? If the first term I'm looking for makes n equals 1, my final answer should be 1. My second term is a 2. My third term is a 3. And what do you know? It seems like whatever my term number is happens to match the actual value. And so we can get a little bit simplified. We can simplify this by saying the general term is equal to the term number, right? I think, again, it's a quick intro. Using that same idea, how about B? Oh, Ian's got something. Ian wrote 5n. And that's absolutely true. If you're not sure, test it. The first term makes the n value equals 1. 5 times 1, that's a 5. And that matches. The second term means n equals 2. 5 times 2 is a 10. And that matches. So on and so forth. It works. And so we can do this. But as I said, some people could have different answers. What if you wanted to rewrite this as Tn is equal to 5 as the first number, but I want to add 5 as we go. I don't want to add any 5 for the first term, but I want to add 5 once for the second term. I want to add another 5 for the third term. So you can say here, if it's T1, 1 minus 1 is a 0. That's basically saying 5 plus 0 is 5. And T2, it's 5 plus 2 minus 1 is a 1, so 5 times 1 is a 5. And there it is. So there's a variety of different ways you can go about it, right? It's just a matter of which one do you think is more efficient. That's all it is. But neither of these are wrong. They're both correct. Okay. Part C. Someone want to give their suggestion for Part C. No? Well, you might have noticed that these numbers are perfect squares. Some of you might have been so fixated on thinking about how to add numbers, plus 3, plus 5, plus 7, plus 3, plus 5, and plus 7. You could have written an equation that matches that, but for now, consider 1, 4, 9, 16. They are numbers that you might have seen for a parabola, and Waylon's got it, n to the power of 2. Whatever my term number is, we're going to square it. So t1 is 1 squared, t2 is 2 squared, t3 is 3 squared. So knowing what term number it is can be very, very useful. And again, I guess another way we can write it, if we were interested in adding, 3, 5, 7. So 1 plus 4, 6, 8. Starting with a 1, maybe I could add 4 times n minus 1 minus 1. Would that work? If that was a 0, no, that wouldn't work because the first number doesn't work. How do I get them to start by adding with a 3? That's plus 3. Of course, that's a n minus 1. But the next number has to be a 5 and not a 6. Hmm. Okay, I'm clearly embarrassing myself, so I'm gonna think about that and maybe I'll get back to you. Okay? Anyways, part D. I'll think about that more after. What about part D? Anyone? No? You might have noticed that the numerator is a 1 and the denominator is a 2. If that's a 2, it becomes a 3. If the numerator is a 3, the denominator is a 4. The denominator is always 1 more than the numerator. And so, starting with the 1, you could have written this. If I'm looking for the first term, it's 1 over 1 plus 1. If I'm looking for the second term, that's 2 over 2 plus 1. Yeah, Simon's got it. That's exactly it. So again, be comfortable with the idea of n, know what that means, and know how that's different from Tn, and we're in a good spot. Any questions? All right. Um, oh, I have to redeem myself. That's gonna bother me. I'll be back with that. Okay. As you can see, there's a whole bunch of questions. As I said before, from now on, it's all just a matter of practice because, again, it's not as much conceptual as it is just having exposure and trying to see what kind of patterns are out there and then solving it. Okay? So the next section is going to be called recursive formula, and that is pretty interesting because it's just another way of writing equations for patterns, for sequences. Now, I'm going to introduce the Fibonacci sequence. Don't look at what that actually defines as. I'd like you to consider it and try to discover it yourself. The Fibonacci sequence is a very interesting sequence, and I'm going to go really fast because I only have 15 minutes with you. It's an interesting sequence because it is a very natural, like, it's a very heavily involved pattern in nature to the point where I would argue that we are psychologically or it's like genetically predisposed to find this particular pattern to be beautiful, to be pleasing to the eye when we see it in nature. What is the pattern here? I'll give you 30 seconds. Just think about it. Any thoughts? Without
Um,
cheating?
it's adding the two previous terms.
Yes. Clara, have you seen this before or have you figured it out just now?
It's the Fibonacci sequence, so
Yes.
it's like used in art a lot.
Ah, yes. See, again, art, it's pleasing to the eye. Let me explain. For the Fibonacci sequence, you actually have to define the first term and the second term, sorry, and the second term, because from the third term on, it's actually the addition of the previous two, right? So 2 is 1 plus 1, 1 plus 1. How about I get a highlighter here? 2 is 1 plus 1. 3 is 1 plus 2. 5 is 2 plus 3. 8 is 3 plus 5. And I think you get the point, right? And so how do we define this? How do we define an equation or a formula that requires the previous numbers for it to work? Well, that's what we call recursive. The root word for recursive being recursion. It means relating to or associated with or coming back from, I guess. The term that we are looking for is a previous term, so notice it's n minus 1, added with two numbers before, so n minus 2. And so if I'm looking for 3, what is So the n value is a 3. What is 3 minus 1? Second term. 3 minus 2? First term. If I'm looking for the 100th term, what is, oh, so the n value is 100. What is 100 minus 2? 98. What is 100 minus, oh, what am I doing? 100 minus 1 is a 98, 9. And then 100 minus 2, 98. This is a Fibonacci sequence. And if you understand how to do recursive formula, we're done this lesson. So I'm going to take 5 minutes just to talk about why this is so beautiful, because it excites me a little bit. The Fibonacci sequence, if you take a look, increases at an approximate rate of about 1.6. So every step of the way, if we multiply it by about 1.6 approximately, we can technically get the next number. Okay? It's not exactly accurate, but it's approximately 1.6, and it's as if nature knows that to be true, not necessarily because it's beautiful, but because it's efficient. For example, let's pretend I have a flower, and then the first two, I see 1 to 1, it's just a flower, right? But from the third petal on, you may notice that the petals begin to grow at slightly off angles from the previous petal. And even now, I'm just sort of guesstimating, but I'm hoping you see that it's starting to look relatively pleasing to the eye. Wouldn't you say that is a sweet flower? Right? Ain't that nice? Come on, someone say, tell me that's nice. In any case, the idea is, as we are rotating, it is spanning out at a ratio of about 1.6, so 60% bigger or further from where it was before. You might have seen this in the internet a lot. I don't know. Depends on what kind of stuff you look up, I suppose. But an interesting example of the Fibonacci sequence is found in snail shells. So you might have seen this picture with a box around it, and then they analyze it by taking a distance from the center of the snail shell and measuring how far away. So let me use an arrow just to prove a point. Arrow, 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 arrow. And every 90 degrees, you will find that the arrow is approximately, I'm going to just say it and say about 60% bigger than it was before. I hope you get the point, right? It gets bigger and bigger and bigger and bigger and bigger. It's not like something in the world told the shell that you have to grow this way, right? It sort of just created this way naturally. Um, why is that? Take the flower, for example. If the petals grew too close together, it's wasting its efforts because two like leaves overlapping each other are not going to collect the same amount of leaves if it spanned out even further and it opens up its surface area. So if it's too cluttered together, one of the leaves is useless while the other one collects all the sun. And so naturally, plants know to spread out further than 1 to 1. Next, if it spans out more than 1.6 as a ratio, it actually wastes space. It opens up too much, leaving gaps in between, and it takes up so much space to the point where it might actually get in the way of other plants, and now there's competition with other plants, and it hurts itself that way. In a very interesting way, everything that we see seems to follow the golden ratio. This 1.6 is a golden ratio. Even if you see artichokes, like I can't really draw an artichoke, but you will see that even artichokes, it starts growing at an interesting 1.6 ratio rate, and it starts to space itself out so that it increases its efficiency in growth. You see a sunflower. Sunflowers have a whole bunch of seeds in the middle. And the next layer of sunflowers, you will see that it's the same size of seeds, but it's spacing themselves out at a 1 to 1.6 ratio. to maximize the space without wasting space, but also spreading out in a way so it doesn't clutter itself, right? It's ridiculous. It's to the point where, again, our eyes are hardwired to find it beautiful. It's to the point where models, if you look at face models or anyone who's like designer model, you may not necessarily say all professional models are really good looking, but you will say that their face is pleasing to the eye. Like there's nothing necessarily wrong with it. And that's because most models, if not all, have a facial structure that is very, very symmetrical. And so, by the idea of ratios, it makes it more pleasing to the eye. Again, you don't have to be necessarily good looking. Makeup can do that. All the people that want, all the what people are looking for models that walk the runway are symmetry. So if you want to test it, and it's not for the faint of heart, I tried it myself and I was clearly disappointed. My face is not the most symmetrical face in the world. I can accept that. Okay, I am not made to be a model. If you want to test it, I've tested it and I realize it's really scary. Take a hand mirror and go to the washroom. Put the mirror right at the middle of your face, right? And then take a look at your washroom mirror with the eye that's available. Your eye that's available will see your face as a mirror image using only one half of your body. If your face was symmetrical, that's what your face would look like. And I was scared because my face was totally different than the original face, which, according to biology, means that I'm not pleasing to the eye. But thank God my wife thinks I'm good looking, so there it is. Okay? Um, Continuing on, the idea of symmetry, it goes past just symmetry. Like if this was someone's eyeball, okay, and that was someone's eyeball, and this was someone's nose, okay, and this was the mouth, okay, there is a specific ratio in facial features that make people's faces look more pleasing or more good looking than another person. And what is that? The closer your face is to a golden ratio, our eyes are automatically sort of predestined to think, oh, that's a really good looking person. Again, this is outside of whether someone is gorgeous or cute or whatever, and whether your boyfriend or girlfriend or significant other is attractive or not. It's outside of that. It's just pleasing to the eye. And what is that? The distance between your eye and your eye should be equal to the size of your actual eyes, right? So this is a 1 to 1 to 1 ratio. And then that should also align with the width of your nose. That should be a 1. And the distance to the lobes of your nose should be about a 1 to 6. And then from there, your lips should also be about a 1 to 6, 1.6 to the distance between your eyes. Any larger, any smaller, blah, 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 blah. It goes on and on and on and on and on. We are hardwired to find the golden ratio to be pleasing to the eye. And that's why I think the Fibonacci sequence is so radical, so wild. Okay? Woo. Any questions before we wrap up recursive formula? All right. So clearly I'm just talking to the wall here. Recursive formula. Because a recursive formula is dependent on a previous term, we have to define the first term for a recursive formula. So for part A, we have to define T1 as -3, and then T2 will use T1 as part of its formula. So how do I get from -3 to 6, and then 6 to -12? Someone want to suggest something? No? Am I actually talking to a wall? Okay, maybe I am talking to the wall. Here we go. If I want to get from -3 and get to 6, I would multiply with the -2. That's -2 multiplied with -3 gives me a 6. Thanks, Murdoch. Okay. If I want to pick 3, I would take a -2 and multiply it with the 6. And for T4, I am going to take the -2 and multiply with -12 to get 24. In other words, the Tn is me taking the previous term and multiplying with the -2. Okay? So a recursive formula needs a previous term in the formula. Let's try B together. B, the first things first, you have to declare what the first term is. That's a 3. What did I do to go from 3 to 5? How do I go from 3 to 5? I added 2. Good. How do I go from term 2 to term 3? Add a 3. How did I go from term 3 to 4? So from 8 to 12, I added a 4. And when you see that, is there a way I can sort of write the general formula? Well, it's the previous term plus n, right? When in doubt, write it out. 2 and 2. Term 3 is the previous term plus the n value. Term 4 is a previous term plus the n value. N. Sometimes writing it out one step at a time will help you see where the numbers sort of coincide. Let's try the next one together. See if we are sort of, coming around. So part C, again, we have to declare what the first term is because without the first term, we don't know, we don't have a previous term to work with. So term 2 would be 5 plus a 6, right? T1 plus a 6, okay, which is 11. Term 3 seems to be the previous term, which is 11, plus a 6. Okay, and I think I see it here. Is the previous term of 17 plus a 6. So that means the term number is going to be the previous term plus 6. So in working to find a recursive formula, your goal is to see how you can use the previous term to help you find the next one. So in a way, you could say it's actually easier than what we've done before. We don't need a general equation. We just take a look at how Tn associates with the immediate previous term. And the rest of this is just homework. Any questions? I think you might have more questions after you try some. If any of these patterns are not working out for you or you get stuck in a homework question, please, by all means, reach out. I am going to direct your attention to here. There's, again, more and more questions where you just practice and get more exposure to the different types of patterns out there. Okay. Yeah. And that brings us to the end. I do want to I request everyone here to put some extra time into Recursive Formula 6.2 because that will help you work out chapter 6.3 better. 6.3 uses this notation of, tn minus 1, tn minus 2, that kind of stuff, right? It uses it up quite often. So get used to it by doing all of these questions. And the textbook, of course. Is everyone okay? Any questions? All right then. Without further ado, everyone don't leave. In case I marked you absent, I just want to triple check something. Uh, F1. Oh, actually, yeah, everyone's accounted for. Everyone's here. Sorry about that. All right. With that said, then, everyone is dismissed. I will see you all tomorrow morning where we get to look at chapter 6.3. Could I show the work I was trying to submit? Um, Patrick, were you able to find chapter 4? I already have chapter 2 from you. It's chapter 4 I'm looking for.
It was the transformations assignment.
Out of 10?
Yeah, that one.
Okay. No, there should be another slot there for you. Stay put. I'll show you where you can find it, okay?
Okay, thank you.
For everyone else, you are dismissed. We will see you tomorrow.